This is further maths, further pure 1 mock paper. We're looking at question 6. This question involves the t formulae. We can tell that because in part A it says using t equals tan 3x. And we've already got an expression up here involving sine 6x and cos 12x. Now, if you're anything like me, the first thing you think of when you see using tan 3x and this expression is that maybe we should convert this expression p of x into something involving t. However, if we look a little further, we'll see that what we're being asked to find is dp by dx. And although it's possible to turn things into t first and then differentiate, because you need to differentiate with respect to x, you would have to adjust by differentiating with respect to t and then multiplying by dt by dx. And that's going to be more of a hassle than doing the derivative first in terms of x and then converting things. So I'm going to start with that. I have p of x. That's 105 minus 20 sine 6x plus 4 cos 12x. And then we're going to get p dashed of x, or dp by dx is probably a better way to write it so that we're clear about what we're differentiating with respect to. And we differentiate this, see what we end up with, and then we'll see how we can turn it into something involving t. So 105 disappears, sine differentiates to cos, so minus 20 sine of something becomes minus 20 cos of the same something. But because the something wasn't simply x, we also have to multiply by the derivative of that something, in other words 6. So this becomes minus 120 cos 6x. And the next bit, cos of something differentiates to minus sine, so we get minus 4 lots of sine 12x, but then we multiply by 12. So altogether minus 48 sine 12x. Now we've got that, it's a little clearer to see what we need to do. To use the substitution t equals tan 3x, we can immediately deal with something like cos 6x, because cos 6x is directly related to the tan 3x. Remember, these are the half angle formulae, as they're sometimes called. The tan of x over 2 is a more traditional way of seeing it, and we can find cos of x when we have tan of x over 2, and in the same way we can get cos of 6x when we have tan of 3x. So this one, if you remember your triangle, is going to come out to something like 1 minus t squared over 1 plus t squared. And while we're here, I'm also going to work out sine 6x. That's going to be 2t over 1 plus t squared. The reason that's helpful is because what we really need next is sine 12x. And we generate that using the double angle formula. So 2 lots of sine 6x cos 6x. That means we're going to need to make use of the two formulae we've just constructed. So one of them is 2t over 1 plus t squared, and the other one is 1 minus t squared over 1 plus t squared. Once we've got those pieces, we can go back to our expression dp by dx and substitute in. So minus 120 lots of cos 6x, that's 1 minus t squared over 1 plus t squared. And then minus 48 lots of sine 12x. Well, we've got quite a lot going on with sine 12x, so perhaps before we substitute it in, we try to write it in a slightly more simple way. For a start, the 2 and the 2 on the top turn into 4, so we have 4t times 1 minus t squared all over 1 plus t squared all squared. So in this form, it's a little easier to put into here. In fact, we can go a step further here, and instead of saying 48 times 4 times something, we just work out 48 times 4, which is going to be 192. So 192t, 1 minus t squared over 1 plus t squared all squared. Now the format they've asked for down here involves a 1 plus t squared squared on the bottom, so it makes sense that we should try to combine our two separate fractions. And what we should end up with on the top for the first one is, well, the minus 120 times 1 minus t squared could be written as positive 120 times t squared minus 1. And I'm also encouraged by that because t squared minus 1 appears as a factor over here in what we're trying to construct. So we have 120 times that, but we also need to multiply by 1 plus t squared for this one. because what we want on the bottom is 1 plus t squared squared. So this is our first of the two fractions now with a common denominator, and then the second of the two already has that denominator, 192t times 1 minus t squared over 1 plus t squared squared. I could also do the same sort of thing in terms of the sign on the top. So instead of 1 minus t squared, I can change the sign to give it t squared minus 1, as long as I also change the sign in front. And that will make it easier to combine these two, and it also helps me to see the common factor of t squared minus 1. So dp by dx becomes something over 1 plus t squared squared. And I am hoping that whatever I get will simplify and factorize to what they've given me, which means I should be on the lookout for common factors straight away. 120 and 192 presumably have a common factor of 24. We can confirm that for ourselves. Remember, 192 was 4 times 48, which can be 8 24s, and 120 is already half of 240, so it's 5 24s. So there's 24 as a common factor straight away. We also have t squared minus 1 as a common factor. And what we're left behind with from the first fraction is 5 lots of 1 plus t squared. And from the second fraction, 192 was 8 times 24. So we're going to end up with 8t. There's not much more to be done with this. And if we've done it right and we've not made any mistakes, we should get exactly what they've got over here. So we could literally just write out what they've got, but it's good practice to use this as your way of verifying all your previous working. So on the top we have 24 times t squared minus 1. It all matches so far. And then another bracket, and on the bottom we have 1 plus t squared squared, which is also the same as what they have. This bracket becomes 5 plus 5t squared plus 8t. And we can confirm that that is exactly what they have. So now we can just write it in, 5t squared, 8t, and 5. So with that, that is the first part of this question. That's part A. The next bit will be making use of this, presumably, to investigate places like the maximum and minimum points of this curve. So here is the second half. This is a fairly common practice with questions of this form. We have the t-formulae describing one particular curve, which might be related to trigonometric functions. And then there's a more complicated function, which our function is modeling, but not perfectly. So the little wobble along the way here is not being picked up by our more simplistic model. But this is the model we're using, so we can tell some things about it. Perhaps our model is going to match well with the larger of the two maximum points and the lower of the two minimum points. So it says figure 2 shows part of the graph of a patient's blood pressure. The blood pressure of a healthy person has a minimum value between 80 and 90 when the heart is at rest, and a maximum value between 120 and 140 when the heart beats. So there'll be moments when the blood pressure drops to 80 or 90, and then moments when it goes up to between 120 and 140. Presumably the extra wobble here is because of the systolic and diastolic process when the heart beats, the lub-dub effectively of a heartbeat, but we don't need to know that detail. All we need to use is the fact that we've got a minimum of between 80 and 90 and a maximum between 120 and 140. And we're using our function p of x to model the blood pressure. So for part B, use the model and an algebraic method to determine whether or not the patient's blood pressure will be considered healthy. Well, what we have here is the derivative. And what we're interested in is the height of the stationary points. So we can say that stationary points occur when dp by dx is equal to 0. That gives us 24 times t squared minus 1 times 5t squared plus 8t plus 5 equals 0. Because, of course, the denominator doesn't come into this. You can think of it as let's multiply by 1 plus t squared squared if you like. Or we can just say if the fraction is 0, the numerator must be 0. This gives us a few different points. We have either t squared minus 1 is 0, or 5t squared plus 8t plus 5 is 0. Now the first of those gives t equals plus or minus 1, but we'll see how those apply. Remember, t is not the same as x, and the time is x seconds. This is particularly sneaky because often we think of time being t, but in this case, t is the default used to represent tan of something. So don't forget what t represents here. This is not 1 second and minus 1 second. This is tan of 3x equals 1 or minus 1. We also have solutions from this quadratic. Those ones, the simplest way to get those is going to be to make use of the calculator. So if we head across to the ClassWiz, we can use menu option A and we can solve the quadratic 585. That gives us complex roots, which suggests there are no solutions for that quadratic. Well, if that gives us no solutions, that must mean that all the solutions correspond to either tan of 3x is 1 or tan of 3x is minus 1. So we just need to investigate each of those. Now, tan of 3x equals 1, that's going to give us values for 3x that correspond to inverse tan of 1. If you don't remember, feel free to use the calculator, but inverse tan of 1, we're thinking about a right-angled triangle where the opposite and the adjacent are the same. So we get a 45-degree angle or a pi by 4. But that's not the only one, of course. You can add multiples of pi to generate more. And each of these will give us a value for x. Pi by 12, 5 pi by 12, etc. Because of the cyclical nature, it's probably not necessary to have lots and lots of different solutions for x. They're going to relate to the same point on the graph, just further along, if you like. So the next wobble in the curve. But inverse tan of minus 1, because of the rotational symmetry of the graph, we should be getting 3x equals minus pi by 4, or 3 pi by 4, etc. That gives x equals minus pi by 12, or pi by 4. Now the minus pi by 12 is negative, so we can ignore that one. So we'll focus on x equals pi by 4, and x equals pi by 12. Those two should give us what we're looking for. Now, what we're actually looking for is whether or not the patient's heartbeat matches what we're talking about, whether at the lowest point is between 80 and 90 and at the highest point between 120 and 140. So we're going to go back up to here and remember that we've got a model P of x. We can make use of this 105 minus 20 sine 6x plus 4 cos 12x to find out which of the points we're talking about relates to the maximum and which to the minimum. So what I'm going to do here is use my old favorite, the table mode. We're in menu option number 9. We can enter in the function. We're going to put 105 minus 20 times sine of 6x plus 4 times cos of 12x. And then I don't need a second function. It doesn't matter what the range is that it gives you because we're able to choose our values based on what we're interested in. What we're interested in here is the values pi by 4 and pi by 12. So I'll put in pi by 12 and I'm going to put in pi by 4. And we can see that at pi by 12 we're getting 108. At pi by 4 we're getting 107. Those look very, very similar to me. So I'm wondering if potentially we get an additional solution if we look beyond. We go to 5 pi by 12. That would be the next thing to check. At 5 pi by 12, at this point I'm starting to get suspicious that my calculator's in the wrong mode. So I'm double checking that I'm actually in radians, and of course I'm not. So I'm going to go back to here and change to radians. We may need to refresh this. So if I press pi by 12 one more time, now we get sensible answers, 81. This is the daft thing you want to make sure of. If your answers are not coming out the way they should, the first thing you check is the simple, obvious things. Maybe you've not been daft enough to leave your calculator in degrees mode, but on the other hand, maybe you have and it's a quick fix. So just have a quick glance at the top to make sure. So I've now put in those two values, and as suspected, going up pi, or in this case, going up by pi by 4, or rather pi by 3, whatever the jump is between these, that doesn't affect the height, doesn't give you new information. It's just maximum and then the next maximum, or in this case, a minimum and then the next minimum. So we can see we've got an 81 for what is presumably the minimum. We've got 121 for the maximum. So what I would do here is indicate where my numbers have come from. So if x is pi by 12, that gives p of x as 81. So this way to write that would be p of pi by 12. And that presumably relates to the minimum point. And p of pi by 4 is coming out to 121. Given that it said we need to be between 80 and 90 as a minimum and between 120 and 140 as a maximum, we can say here, therefore, the patient's blood pressure would be considered healthy. 121 over 81 sounds just fine, and it matches the conditions we were given there. The last part, bonus couple of marks for doing something that is relatively quick to do. We need to consider the patient's heart rate. In other words, how quickly we return to the same point in the cycle. So we don't need to worry too much about exactly what is meant by a heartbeat. But we know that if there's some kind of repeating process, some periodic process in here, then if we just go from one point to an equivalent point later on in the cycle, that will get us back to an equivalent point in the heartbeat, and the length of time that that takes, that's going to be how long the heart takes to beat. Now, our table mode is actually helpful for this as well, because if we think about the values that we were coming out with, here we've got pi by 12, 5 pi by 12 is the next time that we get the same kind of result that we got before. We can see 81. So the minimum happens at pi by 12, and it happens again at 5 pi by 12. So we can see from here what's going on. If we go from pi by 12 to 5 pi by 12, we're going up by 4 pi by 12, in other words, by pi by 3. So it looks like the function has period pi by 3. How else could we have known that it was a period of pi by 3? Let's look back at the original function that we were given. 105 minus 20 sine 6x plus 4 cos 12x. Now the sine 6x is going to give us repetition 6 times as often as an ordinary wave would. So the period of the sine graph normally is 2 pi. If you stretch it by a scale factor of 1/6 in the x direction, we get a period of 2 pi divided by 6, which is pi by 3. The cos 12x, although it feels like it might have a faster period and mess things up, in fact, because cos 12x is related to sine 6x or cos 6x, it ends up not affecting this quite the same way. If you want to convince yourself, you can look at more detail. You can go through here and get a slightly more granular approach. So what we've got here is pi by 12. We get 2 pi by 12 for the next one. 3 pi by 12, and so on. And you can start to see the values as they change. You're effectively plotting the graph as you go along. If this starts to become tedious and you're thinking, hang on a second, isn't there a nicer way? Well, yes, you could go to your table mode, and then this time when you enter your function, you incorporate the fact that you want some kind of pi by 12 thing going on. So you might have 105 minus 20 times sine of 6 lots of, this would be x times pi by 12. This way we can quickly and easily jump up in multiples of pi by 12. And then plus 4 lots of cos of 12 times x pi by 12. And then we can go up. We've got to be careful of brackets for this. How many brackets we're supposed to get. Here we go. So this is now going up in multiples of pi by 12. 1 pi by 12, 2 pi by 12, 3 pi by 12, 4 pi by 12. And you can see how we get back to 81 by the time we get to 5 pi by 12. So we can be confident that it takes 4 pi by 12 or pi by 3 to make a complete period, which means 1 heartbeat takes pi by 3 seconds. We want beats per minute, so we do 60 seconds divided by the time it takes to complete a heartbeat, which is pi by 3, or roughly 1 second, which makes sense. A heartbeat roughly every second is not implausible. And then we just want 60 divided by pi by 3, or if you prefer, 180 divided by pi, which again we can work out on the calculator. 180 divided by pi. And then we can check, based on our own knowledge of pulse rates, whether 57 seems reasonable. 57.3, I think, is the greatest level of precision that I care to go to. 57.3 beats per minute. In fact, generally speaking, 57 is going to be sufficient. You are unlikely to be penalized for a greater level of precision here, but when we have beats per minute, it's not necessary to know it to a greater level of precision than how many beats, whole number of beats per minute. 57 seems reasonable. That's generally speaking slightly on the low side perhaps compared to an ordinary person, but if you're at rest or if you're particularly calm or non-stressed, then you may well have a pulse rate around this sort of level. If you're curious, you can test your own pulse rate, but this basically represents about a beat per second. So it seems reasonable. It's a sensible looking answer, and for that reason, I'm happy with it. We can go back and check to confirm that our answers are reasonable. For the start, from part A, this is exactly what we're asked to prove, so we don't need to worry about that. For this bit, we can verify something here. 0 to 10. This is quite a quick way to check. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 minimum points. So if we've got 10 seconds and there are 10 moments when we've got a minimum point, that fits quite nicely with having approximately 1 beat per second. And that's why having 60 beats per minute, or we've got, which is about 57 beats per minute, seems perfectly plausible.